Hi, my name is Andres Gutierrez, and this is my activity for the assembly and simulation of a four-bar mechanism. So first, my mechanism was a double oscillation mechanism with the values of R1 10 inches, R2 7 inches, R3 3 inches, R4 7 inches, theta 2 at an angle of 60 degrees, and the angular velocity of R2 at 2 radians per second going counterclockwise. And the first step to find theta 3 and theta 4 is to find the value of Z, which is going to allow us to use the law of cosines, which allows us to find all the other angles within this mechanism, which is shown in the procedure here. And then once we have all the other angles, we can use this formula of theta 3 and this formula of theta 4 to find their respective values. And this yields a result of theta 3 equals to 0 degrees and theta 4 equals 120 degrees. And then for the angular velocity of the connecting rod and the rocker, we use the formula of the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. And first we find the velocity of A, knowing that the angular velocity times the cross product of the vector towards that point um, is the value of the velocity of A, and we already know the angular velocity of R2, so we can obtain this expression. And then for the velocity of B with respect to A, we're considering A as a stationary point. And we get this expression where we still have a variable of omega 3, which is the angular velocity of the connecting rod. And we're missing another equation to be able to solve for those values. And we use this expression for the value of the velocity of B. We have that the angular velocity of R4 times the cross product of the vector to point B is equal to the velocity of B. And then substituting the values in this equation, we get the following expression, and we are able to solve for the X and Y components. And solving for omega 4, we have that it is 2 radians per second, and for omega 3, it is negative 4.66 radians per second, which is right, which is just means that our prediction of how the angular velocity was going to look, as we stated it, was wrong, and it goes the other direction. And then for the Excel, I programmed it to give me the values of all the angles, as well as theta 3 and theta 4. And we can confirm these values with calculations done by hand. And this was done utilizing the same formulas as I used by hand and utilizing the law of cosines. And for the Excel, I had to restrict my values to 41 degrees and 69 degrees, utilizing the help of SolidWorks, since my mechanism has dead points and it cannot go full rotation. So I rounded up to the nearest decimal point, to the nearest whole number, and those are the values that I got. And then I did the calculations for the X and Y components of R2 and R4, which allowed me to graph point A and point B, which is point A being the blue point, and then the orange points being point B. And then this is the SolidWorks drawing, which shows us the value of theta 2 at 60 degrees, theta 3 at 0 degrees, and theta 4 at 120 degrees, as well as with the respective measurements that were already given in the problem of the bars. And finally, this is the angle this is the assembly of the real life model. And this shows the angle at 60 degrees, which we can see is exactly the same as the picture, the drawing in SolidWorks, with my name and my ID number. And this is the video for for how it actually moves. And you can see the dead points where it stops. It cannot go any further than that, since that's the purpose of this mechanism, so that it's an oscillatory motion. And we can see, for example, that it reaches a dead point from which it can no longer move, and it has to go back to the other side. So this is my activity, and thanks for watching.